this video, we will solve a famous impossible-looking integral using a clever method attributed to Richard Feynman. The integral is the integral of 1 over the quantity 1 plus x squared, all squared. Before we solve it, let's build intuition. The function 1 over the quantity 1 plus x squared, all squared, is positive and quickly shrinks to 0 as x moves away from 0. Here's a graph of that curve. Now, here is the Feynman trick. Instead of attacking the integral directly, we introduce a parameter, call it a, and create a simpler function. We define f of a as the integral from 0 to x of 1 over a squared plus t squared, dt. We can evaluate this integral in terms of arctangent. The integral of 1 over a squared plus t squared is a standard form. It equals 1 over a times the arctangent of t over a. So f of a equals 1 over a times arctangent of x over a. Now, the key move, we differentiate f of a with respect to a. Because the integral depends smoothly on a, we can move the derivative inside the integral. The derivative of 1 over a squared plus t squared with respect to a gives negative 2 over the quantity a squared plus t squared, all squared. So we get f prime of a equals the integral from 0 to x of negative 2 over the quantity a squared plus t squared, all squared dt. Now differentiate the closed form for f of a. We must use the product rule. The result is negative 1 over a squared times arctangent of x over a, minus x over a squared times the quantity a squared plus x squared. Now, we match the two expressions for f prime of a. This lets us solve for the integral of 1 over the quantity a squared plus t squared, all squared. Divide both sides by negative 2a, and the integral becomes 1 over 2 times the quantity 1 over a squared arctangent of x over plus x over a squared plus x squared. We want the original integral, which corresponds to a equals 1. So we set it equal to 1. Then the formula simplifies nicely. Finally, to get the indefinite integral, we replace the lower limit 0 with a constant of integration. The final answer is 1/2 arctangent of x plus x over 2 times 1 plus x squared plus c. As a quick check, if you differentiate the final answer, you recover 1 over the quantity 1 plus x squared, all squared. That confirms the result. This method is powerful because it turns a hard integral into a simpler one, then uses differentiation to build the harder expression. That is the essence of Feynman's technique. Introduce a parameter, integrate, then differentiate. So that is how Feynman solved this impossible-looking integral by creating a smarter integral with a parameter, then differentiating under the integral sign. This is one of the most elegant tricks in calculus.
Don't forget to like this video, share it with your friends, and subscribe to Knowledge Station. Thank you for watching.